Okay, fantastic. So I'm sure we are all familiar with causal inference, but we might be coming at it from different places. So let's unify the perspective here to set the scene. So this might be an example that's familiar with a bunch of you here. So let's say California passes a smoking tax that takes effect starting in 1989. And we're curious, what is the effect of this per capita cigarette sales tax on for California? So what we can think about here is we can think about the states and the time periods on the Y and the X axis respectively. The check marks indicate the observed values in the absence of a tax, right? So no other state underwent a tax, but California did. So causal inference in the setting we'll be talking about today is the average treatment effect on the treated, and it amounts to imputing what would have happened in the absence of that tax, imputing that red box right there. So after that, we would just take the difference of what we observe, will be impute, and that will be our causal estimate. So here's the primary research question. Can we bring flexible estimation from machine learning to these causal panel settings? Even in the example before, we have only a couple of time periods and only 38 states in that panel. So the spoiler is, yes, we can. And so how we're going to do that, we're going to leverage the structure of the data in a specific way. So the way that we utilize the structure of the data, how we put it together in some ways, and the data input matters. In addition, we're going to introduce a machine learning architecture that can work well on these data sets, empirically on placebo tests. And we're going to show that this proposed approach generates estimates with substantially lower root mean squared error than common estimators. This is again on placebo tests, and I'll explain that a little bit more. And we're also going to explore it under simulations, but given the time constraints, I don't think we're going to get to that today. So formally, we're going to be adopting the potential outcomes framework. And again, the causal estimate of interest is the average treatment effect on the treated. So let's just abstract away and let's talk about what's been done and how this inspires our approach. So let's think about one treated unit, unit N, and one period treated, so period T. What has been done? So we can think about the synthetic controls literature, where what they do in essence is a constrained version of this vertical regression. So what we're going to do is we're going to assume that the pattern sort of across units is stable across time. So what I can do is I can learn a set of weights in this dark blue here and apply those same weights in the post period. And in this way, I leverage information sort of only in this one unit directional way. The flip side of that is synthetic controls literature. The flip side of this is I can obviously go the other way around as well and learn a set of weights and apply those weights there. This assumes the opposite relationship, which is that the relationship across time is stable across units. So this might not look quite like unconfoundedness, but it kind of is if you think about imputing the sort of learning a conditional response function and imputing that for the other unit. Another way you could do this is you can sort of leverage information across the panel in both directions simultaneously. So this falls under the umbrella of two-way fixed effects estimation, or more generally, factor models. So what are we going to do here? We're going to translate this into a supervised learning problem. So what we're going to do is we're going to use this sort of L-shaped pattern. We're going to use contemporaneous controls, that is like the vertical component, and we're going to use the lagged outcomes, which is the horizontal component here. And what we're going to do is we're going to try to impute that purple square, and we're going to create a training set, and then we're going to predict out of sample. The number of lags here is a hyperparameter that one can tune via cross-validation or whatever your favorite way of tuning is. And we're going to use an architecture called NVeats from the forecasting literature, and we're going to adapt it so that we can use the data sort of inputs in this way. And we're going to coin this, just for our future results, we're going to coin this NVeats because we're doing synthetic counterfactuals. For the sake of time, I'll go into the model architecture only after the conclusion we get there. What are the results? Let's first compare it to the most common methods that we see. So we're going to be evaluating our performance on two real data sets. One is going to be the California Prop 99 data set, which I described earlier, and the other one is the another common one, which is the West Germany reunification data set. And so in both of these, you don't have that many time periods and you don't have that many countries or states. So these are relatively small data sets where synthetic control has been traditionally used. So how are we going to evaluate our performance? We're going to do two different placebo tests. One is going to be pseudo-treated states. So what are we going to do here? We're just going to get rid of California entirely. And what we're going to do is we're going to block out, we're going to pretend, for example, Alaska was treated. And then we're going to predict for Alaska. And obviously, because the effect is actually zero, we know based on root mean squared error how close we're going to get to estimating or recovering that effect. So we can do that for Alaska, we can do that for Colorado, so on and so forth. And these are the results that we see. So for Prop 99, this is the error distribution across the remaining 37 states, I believe. So in red, we have two-way fixed effects. In green, we have synthetic control. And in our method, it is in blue here. So for the 1 year out predictions, this is what we get. And so we're a little bit more tightly concentrated around zero than these other common estimators. And yeah, this looks pretty good basically for us. Right? It suggests that this method actually can work. And if we decide to go 5 years out, we're still, the most tightly concentrated around zero, although obviously as it's a forecasting methodology, it's harder to predict the future. So I guess one of the limitations here would be, if you're only interested in the short-term future, this might be a good tool. The other exercise we can do is pseudo-treated years. So instead of, so what we can do here is we're just going to take California only and block out 1988, block 1987, 86, et cetera, go backwards in time in that way. And this is what the error distribution looks like. So these are iterative 1 year predictions from 1975 to 1988. And the notable thing here is that if you're predicting 1975, you don't have a lot of training data points at all, right? Because I'm using lagged outcomes as, sorry, so the data set starts in 1970. So if I form my training set where I only use one lagged outcome, for example, I'm only going to have 4 training data points, right, to predict 1975. And, it's a deep neural network architecture. That's kind of a surprising thing. You'd expect it, perhaps to perform horribly. So this is kind of one of the more surprising things that we found. Using this architecture, we're doing pretty good. And obviously there's a skew, which perhaps can be explained by the fact that cigarette sales were falling at a rate faster than any of these models could have predicted. The 5 year, of course, is a little bit noisier, just like we saw in the other placebo exercise. So this is the summary. Across the board, if you compare against two-way fixed effects or synthetic control, we're doing a lot better with mean squared error. I'm sorry these numbers are not like standardized, but at least relatively you can see, at least on these placebo exercises, we're doing quite a bit better than synthetic control. So how do we compare though against more recent methods that have come out? So two of note are synthetic difference of differences, which combines a synthetic control type approach with like a difference of difference approach. And in that way, sort of leverages information in the panel sort of along both axes. And another one is matrix completion, which again utilizes information along both axes simultaneously. So if you look at the two, we do both of the synthetic difference of differences in our method perform better than matrix completion. But if you look at the numbers, we get pretty close to synthetic difference of differences. I've highlighted, our numbers in bold, and it looks better. But if you look at the magnitude, it looks like it could maybe be within noise. If this were a different data set, perhaps, it might have changed. But regardless, we do pretty well. So a lot of our work in this paper was exploring sort of when under simulations, when did synthetic differences, when you might want to use that method, for example, over ours. And maybe as expected, one of the things we found was, if most of your outcomes can be explained by sort of like fixed effects, for example, if fixed effects contribute a lot to sort of your outcomes, then something like synthetic differences, which explicitly builds that into their framework, would do a little bit better. But under like interactive fixed effects model simulations and a bunch of other different types of real world calibrated simulations, we saw that our method ended up on these placebo tests at least doing a little bit better. So one other thing you might be worried about is, well, you have this arbitrary neural net, you might be overfitting, for example, or you might be incurring bias and regularization. So this falls under the whole debiased machine learning literature. So what we can do here in order to fix that is we can estimate the bias simply by using our estimator, but then, using our estimator there on the left-hand side, and then training sort of a second estimator on the pretreatment period by splitting it in half, estimating the bias on the second half of the pretreatment period, and subtracting that off. And you can show that basically the difference converges in probability to 0. So, and this diagram here just shows that the bias correction does help in these settings, but does explode the variance, which is as expected. Okay, so I've talked a lot about, hopefully I've convinced you that this method does work pretty well in these real data sets. A good question though is like, well, this is sort of like a black box in some sense. Where do the gains arise from? So I've talked a lot about how we use the data inputs in this like L-shaped pattern. And I've talked about how the architecture matters. So let's first look at how whether or not the architecture matters. So we're going to use the inputs in the same way. We're going to use like this L-shaped sort of a thing, but we're going to use a simple model, like an OLS. So instead of complicated architecture, what can we get just from the lagged outcomes with the contemporaneous controls? You can write it sort of in this way, right, where your outcome is equal to, your lagged outcomes sort of plus the contemporaneous controls. And I think like a natural benchmark here is synthetic controls, which is kind of like 0 lagged outcomes and some sort of like restricted OLS. So if we take synthetic control and we get rid of the restrictions, right, where the weights have to sum to 1 or, all of these sort of constraints, you already get some gains. And these are root mean squared errors. And then if you introduce lags, you can get even more. So with added flexibility, you already get some gains. And this is the simplest of models. This is just like a regular OLS. However, if we were to just then say, hey, let's just use machine learning, let's do like random forests or neural nets, these, as expected, perhaps on a data set like this, don't really perform very well. So that's neural networks and random forests. In contrast, using this architecture, you get substantively lower root mean squared error. That first one, however, we'll talk about in a second, but with the lags put in there, you do pretty well. So on the flip side of that, we can think about, well, let's actually, instead of using sort of like information in both directions to make that L shape, instead, why don't we use this complicated architecture, but only go one way? So in like a pure time series forecasting way, or kind of like a synthetic control sort of way. So what do we get when we do that? So if we do using lagged outcomes only, we have like the pure time series forecasting way. So that's that first row right there. You do pretty well. You don't do as well as, like synthetic differences, but you do decently. And if you don't include any of the lags, you end up sort of at a magnitude similar to if you were to just use some sort of MLP regressor or like some neural net, whatever. And so it does matter that you use the data inputs in a specific way. That's what we find, at least on these two data sets and under simulation. So to conclude, We've proposed the deep learning model to help construct counterfactuals with lower mean squared error. And we showed that using information in both directions matters. Showed evidence of success on real world data sets and simulations. I did not show the simulations, but happy to in the appendix. And we've done some exploration into understanding when this method succeeds, as well as where the gains arise from. Do I have a little bit more time? 2 minutes. Great. I can talk. I'm sure people are probably curious about the architecture. I saved this slide here. So this architecture is a little bit special. So you have this input, right? Whatever data input you want, and it's going to go through sort of a sequence of blocks. And in every single block along the way, you're going to have this sort of like a residual structure where you're going to produce a partial forecast, and you're going to also produce a backcast. And so what you're going to do is whatever backcast you produce, you're going to subtract that off of your input and feed that residual into the next block. So you're iteratively mining the signal. And this has some resemblance, I think, to like the boosted trees. And so I think therein lies sort of the success of such an architecture. Boosted trees by themselves, by the way, don't do as well as something like this. But I think like the intuition behind why an architecture like this matters is that it can iteratively sort of mine the input signal. And so even if you have a very small data set, you're still able to get, something out of it. Anyway, so